A2 Further Maths, Mid-Ordinate Rule and Simpsons Rule. So what we're going to look at is we're going to look at two numerical methods for integration. Now you've actually seen a numerical method for integration already in your normal maths called the trapezium rule. So what we're going to look at is two alternatives to the trapezium rule. They do exactly the same job as the trapezium rule, they're just different techniques, different rules. Okay, the first one we're going to look at is what's called the mid-ordinate rule. Now if we look at a similar sort of setup to how we've done numerical integration before, if we want to approximate the area under this curve between the limits 0 and 3, and we're going to look at using 3 strips. Now a lot of this seems to be very similar to what you've seen before with trapezium rule, and they do share a lot of similarities. So for example, in this case, we know that 3 strips means that there will be 4 ordinates, with the ordinates being 0, 1, 2 and 3 in this case, equally spaced out, and those 4 ordinates will produce our 3 strips. Now for the mid-ordinate rule, what we use is the name itself to give us a reminder of what to actually do. It is the middle of the ordinates. So if we look at these bits here, and we look at the first 2 ordinates, which is 0 and 1, and we're going to look at the middle of those 2 ordinates. So we're looking for somewhere in the middle, hence the mid-ordinate. So we literally put in whatever value would be in that middle. So between 0 and 1 will be a half, as we know. We put that into the function, and that would give us our height at that point. And that is why we get the mid-ordinate from. Once we do that, we form a rectangle. So it's a nice easy shape. And yes, we've missed this part out here, but we also know that we gain it there. All right, that will always happen. You'll lose a part on one side and gain another part on the other side, unless it is a straight line, of course. Now we could do that for each of our strips. So we've got 3 strips. So we've done the first one. The second one, normally what we do is we substitute 1.5 in. That would give us our mid-ordinate height, and then we can use that to form our rectangle. And we'll do that again on the third strip. We go up till we get a y value, so we'd substitute 2.5 into our equation. We'd get our y value, and that would give us our height. And as you can see, in each case, we've lost a bit of the area there, but we've gained a bit of an area here. Okay, so it's a fair numerical analysis, or approximation, I should say. So we're going to repeat this for each of the pairs of ordinates. Yes, we have. So we're looking for the integration between 0 and 3, and it is approximately the area of that first rectangle. So in this case, it has a base of 1 and a height going up to whatever the y value at 0.5 is. Now that 0.5 there is because it's in between the first ordinate and the second ordinate. The first ordinate is y0, the second ordinate is y1, hence y 0.5. It's not to do with the fact that it is a half. So this one, y 1.5 times by the width of 1, and the last one between the ordinates 2 and 3 would be 2.5. Once we've got the values of each of those, we can add them up, and that is an alternative way of writing it by bringing out that number 1. Yes, in this case, which is a rather simplistic example, we can see that the value of the width is just 1. Now if that was anything else, it's just demonstrating you can always pull out the width of each of the rectangles, because there's always going to be exactly the same width. Okay, so grab your notebooks. Let's just formalise this and put it in our notebooks. Notice I've changed the limits to A and B, more general, and got rid of my numbers. So if I want to find an approximation for the area between the limits A and B. So if I'm looking for the area, or an approximation for the area between the limits A and B, then I need to do a couple of things. First thing I need to do is obviously I need to know the number of strips, which we'll call it a generic value n, a general value n. And I want to work out the width of the strips. So if I know the number of strips and I know the limits at A and B, I should be able to calculate what h is. All right, so have a think about that. See what you get. Okay, you'd be right in saying that it's going to be the difference between these two divided by however many strips you had. So the previous one, it was 3 take away 0 was 3, divided by 3, which gave us a width of 1 each time. Okay, that formula, as you know, you've seen before, it's exactly the same for trapezium rule, and it's given to you in your formula book. All right, so you don't need to learn it. So the mid-ordinate rule again, as given in your formula book, so you don't need to learn it off by heart, but you do need to learn how to use it, is given as this, where a and b are our limits, y is whatever formula we're using, whatever equation we're trying to work out the area under, h is the width of each of the strips, and then each time you're looking at the middle of each of the ordinates. So we're looking for the middle of the first two ordinates, y0, y1, middle of the next two ordinates, y1 and y2, and so on up to the one before the last. So yn minus 1 and yn being the last would be yn minus 0.5. Okay, so let's have a look at an example with some numbers in. So get the question down in your notebook. So use the mid-ordinate rule with 5 strips of equal width to find an estimation for the integral of 5x over ex squared dx between 1 and 2. So it's not a very pleasant thing to integrate. And that's the whole reason why you need numerical integration, is because if you're looking at a numerical integration on an equation that you can't integrate, then it will give us a very good approximation of what you should be getting. Okay, so pause if you need more time to write it down, or if you want to quick go yourself, and then we'll have a look through the answer. So in this case, the first thing I want to do is work out the h value. You work out the h value anyway, because there's a good chance in that exam you'll be given a mark at least for getting the width of the strips. So I've noticed a couple of bits of information. There are 5 strips. My a and my b value are 1 and 2. So I'm looking for, just using this formula, b minus a, so I've got 2 minus 1, all divided by 5 strips. Just be careful in case they give you ordinates. They might quite easily give us 6 ordinates. You always divide by the number of strips though. Right, so that is going to be 0.2. My numbers are going to go up in 0.2s. So what I'm going to do is just write down the actual ordinates themselves. So I know that x0 is going to equal 1, x1 is going to equal 1.2, and so on. And hopefully, if it works out right, I should have 6 ordinates, because there's 5 strips, and I should end perfectly on 2. So it's a good check to see if you got it right. So 1.4, 1.6, 1.8, and 2. 1, 2, 3, 4, 5, 6 ordinates, and of course in between those 1, 2, 3, 4, 5 strips. Now, because I'm looking for the mid ordinates, what I don't want these values at all. I want the ones in between. I want the x 0.5, x 1.5, and so on. So I'm going to write down the mid ordinates, and then I'm going to write down the corresponding y values. So for example, first things first, let me make sure I'm aware of which x values I want. 1.1, 1.3, 1.5, 1.7 and 1.9. So I've considered the middle of those ordinates, the mid ordinates. And I notice that I should have the same amount of mid ordinates as the number of strips. That should always be the case. Right, so to find the y values, which I need for the formula, I'm just going to put those x values into here. So I'm going to do some number crunching. I'll save you some legwork. I'll do it for you. So take 1.1, put it in for these 2 x values, and out pops our y values. So working to 4 sig figs here. So y 2.5, y 3.5, and y 4.5. Okay, make sure you got some stuff you need before we move on. Okay, so now that I've got the y values, what I can do now is I can actually write down the formula and work out the actual value, the approximate area, or the approximate value of that integration. So the mid-ordinate rule states this. You don't need to copy it down, it'll be in your formula book. And I just need to fill in some of the gaps. So I know that h was 0.2, I know that y 0.5 is down here, and so on. So I'm literally going to just write down these 5 values inside that bracket, and the h value being 0.2. And if I do that, notice I've replaced these parts just for my y and my a and b. I can just grab my calculator, I can type it all in, and out comes 0.872 to 3 significant figures. Okay, so always go to at least 3 significant figures, never less. So 0.872 is your approximation. Again, pause if you need to. Okay, so just before we move on to some questions yourselves, what I'd like you to do is just have a quick look at that that graph, you can see that I've used the mid-ordinate rule to approximate the area underneath it between these two limits. And what I'd like to consider is whether the mid-ordinate rule is an overestimation or an underestimation. So just pause there, have a think about it, make sure you're using the right key language, and just see what you think. Is it an overestimation? Is it an underestimation? Okay, so hopefully you've noticed that it does depend on the shape of the graph. Okay, when the graph's in the middle here, it looks like a point of inflection just there, then they are very, very similar. Okay, but if the graph is up here in a sort of concave position, they are slightly different. That looks smaller than that piece, so it's probably got more on that bit than that bit. So let's have a look at just drawing that. On that concave section, we notice that that bit is what we added on, but this part is what we took away. So it's quite clearly an overestimation. In a concave section, the mid-ordinate rule always produces an overestimation. Whereas in this section, where it's convex, right, when it's curving round, we can see it's the opposite that's true. Okay, so although we've added this extra bit on and we've missed that part out, we can see that it's an underestimation of what we wanted. Okay, the bit we added on was smaller than the bit we actually forgot to add on. Right, or couldn't add on because of the mid-ordinate rule. So it depends on whether it's concave or convex. It's also worth remembering that it is the opposite to the trapezium rule. So when we did the trapezium rule, and you could talk about the concave and the overestimation, the underestimation, it was the opposite way round that was true. Okay, that when it was concave, it was an underestimation, and when it was convex, it was an overestimation for the trapezium rule. Okay, so before we just move on to some questions, what we're going to look at is the other numerical integration, which is called the Simpsons rule. So the Simpsons rule is a bit more technical than the other two, because unlike the trapezium rule, which is quite basic really, you take 2 points and you draw the trapezium and do estimate it from there. Okay, so it's quite a basic sort of thing, the trapezium rule. The mid-ordinate rule, no better really. You find the middle and you draw a rectangle. But the Simpsons rule is slightly better than that. What the Simpsons rule does is it takes 3 points. It takes the 3 points, 3 of your ordinates, and instead of just trying to draw trapeziums, it knows it's going to be a curve. So what it does is it tries to form a quadratic curve that fits those 3 points. So 3 points can be used to form a quadratic curve. And the quadratic curve is a lot better approximation than using straight lines. As you can see there, yes, it's not perfect. Yes, it's got an underestimation and overestimation, but generally it's a lot better than just joining these two up and joining the trapezium rule. So it's the best out of all of the numerical integration techniques. But it's also the most complicated to actually. Okay, so just grabbing your notebook then, we'll write down your last numerical integration technique and make sure you've got the Simpsons rule next to it. So if I want to look for an approximation between the areas, for the area between these two limits, a and b, so an approximation for the integral, I need to work out the number of strips, and you can see with each of these strips that the approximation is very good, right, because it's a curve rather than straight lines. But one thing that's important to realise with the Simpsons rule is the n has to be even. You have to have an even amount of strips for it to work. All right, so although it's not difficult to easily make sure you can use the Simpsons rule, for example, if someone said I've only got 5 strips, you can easily amend it to 6 strips and therefore use the Simpsons rule. What you might find is an examiner might ask you a quick question, why can't you use the Simpsons rule for this? Maybe on the back of a mid-ordinate rule question, for example. So just remember that n has to be even. The width of the strips is calculated exactly the same as it would be for the other two approximations. To work out the h, because they're all equally spaced out, b minus a divided by the number of strips. So that part stays exactly the same. So you don't have to learn that 3 different ways. It's always the same for the width of the strips. Once you've got the width of the strips, the formula for the Simpsons rule looks like this. Okay, so you can see written very similar to start with, but then there's a slightly different setup on how it works. So you've got the third times by the h, you've got y0 plus yn, 4 lots of some of the other terms and 2 lots of some terms. Okay, so just pause there and take down what you need, and then we'll have a look at this formula in a bit more detail. Okay, so really, what are these terms on about? Well, the first two are just literally your first term plus your last term. So when we come to looking at our terms, the first number and the last number are added in first. Once you've done the first term and the last term added together, then you do 4 lots of all the odd terms. So the y1, the y3, the y5, the y7, all the odd terms, they'll appear 4 times. Once you've got all the odd terms, what you should be left with are all the even terms, y2, y4, and so on. Now, it's important to realise that you do not repeat the first 2 terms. That's the common mistake that happens. So, for example, if y6 is your last term, you do not include it in here. Hence, it's telling you here 2 away from the last term. Okay, so what you should find is that you should use every single one of your terms once and once only. And I'll repeat that in a minute, because a common mistake people make is accidentally using the even terms twice in here. Right, that bit of information is important. You're expected to know how you can improve the Simpsons rule, the mid-ordinate rule, and the trapezium rule in normal maths. And the easy answer to it, you can improve it by just including more strips. If you can increase the number of strips, you can therefore increase the accuracy of the approximation. The problem is, the more strips you include, the more work you have to do with the numerical crunching. So, let's have a quick look at Simpsons rule questions. So Simpsons rule with 7 ordinates. So before you start screaming at me and saying you said we had to have an even amount of strips, there's nothing wrong with 7 ordinates. To approximate that equation just there between the values of 2 and 5. So just pause there. Again, you might want to quick go yourself, or you might want to work through the model solution with me. Alright, so let's see how far you got then. So the first thing we want to do, same as always, let's work out that h value. So it's top limit, take away bottom limit, divide by the number of strips. Be very careful. Easy mistake to make, divide by 7. No, n is the number of strips, not the number of ordinates. So we know because we've got 7 ordinates, that is the same as 6 strips. So n is definitely going to equal 6. Okay, so what we got, 5 take away 2, 3, divided by 6, 0.5. We are going up a half each time. Draw your table of values. So you might have preferred to do this with the previous one. Some students prefer to have the set table every single time. So the x and y table, I'll put my x values in, but I need to be aware of which ones they are. So I've got x0, x1, x2, right up to x6. All right, 7 ordinates. 1, 2, 3, 4, 5, 6, 7, but 6 strips. So the first term is going to be 2. If I go up in 0.5s, I should end at 5 if I've done it right. 2.53, 3.54, 4.5, perfect. Look at that. It works out perfectly. So then I can now work out my y values. So my y value, which of course is that part just there, my y values, I substitute each of these numbers in. So put 2 into it, put 2.5 into it, and it's going to give me y0, y1, y2, and that was what I need for the formula. So there we go. I'll do the number crunching for you, save you a bit of legwork. To 4 significant figures then, each of the values have been calculated. Okay, so I've worked out the h, I've worked out my x and my y values, so I've got all my ordinates sorted. What I can do now is write out the Simpsons rule for the formula book and fill it in. Okay, so I'm looking for the integration between my 2 values. A third times h, I've got my h, it's there. First term plus last term. So the first term is 31.94, last term 5.701. So I can certainly put those 2 terms in first. Okay, and I would not be using them again. They are done. Ticks them off. 4 lots of all the odd terms. So the y1, the y3, the y5. So 4 lots of each of those. And again, they're ticked off. I won't be using them again. Plus 2 lots of basically anything you haven't used. So I haven't used those two, the Y2 and the Y4. So I write those in. Just double check. 1, 2, 3, 4, 5, 6, 7 numbers, 7 ordinates, 6 strips. And each of those has been used once. It's always a good idea just to double check, make sure that everything's correct. Once we've got that, we can grab our calculators and we can type in a third times 0.5 times all this stuff. And the approximate answer, 36.7 to 3 significant figures. Okay, never go smaller. Okay, so what I'd like you to do then is have a quick go at the exercises on those 2 pages. So you're practicing your mid-ordinate rule skills and you're practicing your Simpsons rule skills as well.